So in the last video, we talked about what does it mean to be continuous. And in this video, we're going to look at kind of the opposite side of the coin. What are the different ways you can be discontinuous? All right, so we're not continuous, but what could possibly go wrong? So the first one is kind of the nicest case of removable discontinuity. All right, it occurs when the limit exists, but one of two things happen. Either the function value doesn't exist, or the function value exists, but it's not the same as the limit. So one example could just be a graph like this. The limit's going to exist at this value a, but there's no function value, there's no closed-in circle here. Or we could have something similar, right, at a. But there is a function value, it's that closed dot, but it's not the same. So these are the kind of two removable discontinuities. They're called removable because if I just kind of filled in this hole, it would fix the discontinuity. If I kind of just move this dot down to there, it would fix the discontinuity. So removable in the sense that I could kind of fix it by just filling in one single spot. But if the limit exists, that pretty much means you have a removable discontinuity. All right, a jump discontinuity, it's just like when we were talking about limits not existing. So if you have any type of jump in the lines of your function, that's going to be a jump discontinuity. And just notice this is not removable because I can't just fill in this dot up here. That doesn't fix a jump. I would need like an infinite number of points to fix the jump, which isn't possible. All right, so for this one, it's not possible to remove it like in our last one. So we just had this big jump. And another one that's kind of related to the limit not existing is limits don't exist when we have asymptote. So an infinite discontinuity occurs when there's an asymptote. So again, the kind of tip is I have to lift up my pencil once I get this asymptote. So it's not continuous because the limit doesn't exist. All right, so those are our three types of discontinuities. All right, removable, jump, and infinite. And you can see they're kind of related to when limits don't exist. All right, that was a question on our Unit 1 test. So now, all right, we have this discontinuity x equals 2. We saw this in the previous video, but what type of discontinuity is it? Well, basically we have to figure out, is the limit exist? All right, is there a jump? Is there an asymptote? So really for this question, when you're looking at rationals, there's no jumps in rationals. So you're asking yourself, is there a hole or is there a asymptote? And the way we do it with rational functions is that we can factor and simplify. If we can simplify the kind of bad thing away, then it's going to create a hole. If the bad thing doesn't go away, then we get an asymptote. So for this function, we can factor the top. All right, like that, using the difference of squares, and we can see we can cancel out this common factor of x minus 2. All right, so this function is, I'm going to put the squiggly equals because it's not exactly equal to this function, but it's basically equal to x plus 2. All right, so the limit as x approaches 2 of f of x, that's a 2, not a 7, means I can just plug in 2 into the simplified version. And that's going to give me 4. All right, so this limit does exist. All right, I can find the limit, which means this is going to be a removable discontinuity. All right, because whenever the limit exists, it's going to be removable. I can kind of fill in that hole in my graph and make this actually continuous if I was able to fill in that hole. All right, so for this one with rationals, basically if this factor, this bad factor here gets canceled out, that's going to give you a hole, and then you get a removable discontinuity. What about this one? I had a similar problem. I would try the same thing. And we can factor the top using the difference of squares. But in this case, nothing cancels out. So no matter what, if I try to plug in 3, this thing at the bottom is still going to give me 3 minus 3, which is 0. The top would give me, 3 minus 2 is 1, give me like negative 5. All right, so I get a number on the top and 0 on the bottom. And in our previous things, we saw that when this happens, we have a number divided by 0. That's going to give us an asymptote. So this is, oops, that's not what it's called. For our discontinuity, this is an infinite discontinuity, right? Because we get an asymptote. So really this is just kind of going back to our different types of asymptotes for rationals. All right, if we are able to cancel out factors, we'll get removable discontinuities. If we can't, and this kind of factor is left on the bottom, we'll get an asymptote, so we get an infinite discontinuity. All right, so these are the kind of main types of discontinuities. Well, they're the only types of discontinuities and the kind of the ways that you'll see them in questions related to rationals.